All right, so in the previous video, we have seen that this equation is actually a singular perturbation of a problem, because we add a small perturbation here that changes the type of the equation. Indeed, in the unperturbed case, there's only one root, and in the perturbed case, a second root is coming because we change the degree of the polynomial from 1 to 2. And so we have observed that there's one root, the second root, actually, that comes into the problem coming from infinity, minus infinity, in fact, in this case. And we have discovered in the previous video that when this root is of order 1 over epsilon, it seems that it works fine in our derivations. And this is, by the way, something we have obtained by doing the asymptotic expansion of the exact solution of the problem. In that case, we could get the exact solution of the problem, which, of course, could just confirm that 1 over epsilon is the right order of magnitude for the root, but it could also have been 1 over square root epsilon, which is large, could have been 1 over epsilon square, which is also large, or any other power with n larger than 1, n positive, could have actually done the job. So what we do in this video is to understand how do we determine the order of magnitude of the large roots. All right? So how to know the order of magnitude of the large root. Okay, and so I'm going to discuss two different methods for that. The first one is called pairwise comparison, and the other one is a generalized version of pairwise comparison. Okay, so I'm going to start with the pairwise comparison first. So we need to observe that in the governing equation, a leading, so I'm talking about the leading order of magnitude, we need at least two balancing terms. Okay, demonstration. Because if it was not the case, very easy. Let's just imagine that these at the leading order, only one term is much larger than the others. Let's imagine this is of order 1 over epsilon, and let's imagine this is of order 1, this is of order 1. So we have something large, and two terms are small. So if this one is large and the other two guys are small, when you will rewrite the governing equation at each order, you will end up with one term being equal to 0. And because we're dealing with polynomials here, one term is equal to 0 means that x itself is equal to 0. And if it's equal to 0, it's not a solution that we are interested in. All right, because we remember, keep in mind that the coefficient of the leading term needs to be different from 0. All right, so that's something that is totally general. Two balancing terms in the leading. And that's something we're going to exploit in the pairwise comparison. Okay, so how does it work? It consists in identifying the two terms that balance each other or more that balance each other at leading. All right, so because we have three terms, we need to find three terms in the equation. We need two terms to be combined. So in total, the number of terms in the combination is Cn2. All right, this is the number of possible combinations. When there's only three terms, this is quite easy. We have three options, either epsilon square and x, either epsilon square epsilon x squared and y, either x and 1. Okay, so we have 3 cases to consider. I just use a 2 by 2 or pairwise comparison. And I said, okay, let's assume these two terms, epsilon x squared and x, are leading and have the same order of magnitude. So these two terms are leading and have same order of magnitude. If they have the same order of magnitude, it means that epsilon x squared has the order of magnitude of x, meaning that epsilon x, if you just recognize that x can't be something equal to 0 or cannot have order of magnitude equal to 0, we can just virtually divide left and right by x. It means that epsilon x is of order 1, and it means that x is of order 1 over epsilon. Wow, great, that's exactly what we were expecting, right? So it means that one possible way to get two terms balancing each other is to have x being of order 1 over epsilon. There's something else we need to check. We need to check that by doing so, the orders of magnitude of the different terms is such that these two are well leading, okay? So let's keep going and say if x is of order 1 over epsilon, order of magnitudes of the terms, I'm going to use them in the same order as we had before. So epsilon x squared then will be epsilon over epsilon squared, which is 1 over epsilon. The second one will be x, that is 1 over epsilon. And the last one is 1, which means 1, of course. And so we do observe that who is leading? This is leading, this is leading, because 1 over epsilon is much larger than 1. All right, so we were right. We were right to say that these two could balance each other, and this is a solution that we could keep. And in that case, the order of magnitude of the equation is 1 over epsilon. By the way, that's something we already have discussed in the previous video. So just by multiplying, in that case, the equation by epsilon brings it back to something that is of order 1 at the leading. Okay, second, let's assume that epsilon x squared and 1 can balance each other. In that case, that would mean epsilon x squared is of order 1, or x is of order 1 over square root epsilon, which is also a large root, and why not? That could be the root we are interested in. Okay, we need to check that these two terms are well leading, and if I assume that x is of order 1 over square root epsilon, the order of magnitude of the terms, they become epsilon x squared. This is of order 1. X is of order 1 over square root epsilon, and of course 1 is of order 1. What do we see here? This one is leading. Okay, so it means that if x of order 1 over square root epsilon was a good order of magnitude for x, when we look at the balance between the different terms in the governing equation, we do observe that indeed there is a possible way to have the first and third term balancing each other, but they do not balance each other at the leading order. And at leading order, there's only one term. So clearly this shows that this is not a good scaling for x, because nothing would balance the second term. All right, so this solution is to be rejected. Last but not least, third option, we assume that the last two terms balance each other. This one is simpler because it would just mean x is of order 1. And if x is of order 1, then we have epsilon x squared is of order epsilon. X is of order 1. 1, of course, is of order 1. And then we see that we have the two leading terms over here, and the other one is much smaller. So we have a second possible order of magnitude for the root of the problem. And that's exactly it, right? So this is what we studied before. This is root 1, showing that for this one, you can use a regular ansatz. That's what we did in the previous video. And for the second root, you use a regular ansatz after rescaling. Use rescaling. Define x tilde is equal to epsilon times x, or put it differently, just say that x, because it's of order 1 over epsilon, just say it is x tilde over epsilon. All right, substitute this in the governing equation and then use a regular ansatz after rescaling. And then the problem is solved. All right. So pairwise comparison, this is a great approach when the number of combinations to test is not too large. Okay, not too large. Well, it's something that just depends on how patient you are. Usually I'm not too much, so 3 is fine, but if I need to go higher than 3, then I would just quickly get bored. And this is why I have devised another method which could also be more efficient as soon as there are many more terms in the equation. And I want to share this one with you, which is a generalized pairwise comparison. And this one works really good, really well and really fast, no matter the number of terms you have. Okay, let me just write here. This one is great, even when the number of combinations is large. All right, and so how does it work? I will just say that at the end of the day, we will need a rescaling. Probably we'll need a rescaling, especially if we're looking for large roots. All right, so let me just say that x is going to be written in the form epsilon to a certain power, which could be -1 in our case, multiplied by x tilde. All right, and I just assume that x tilde is not equal to 0 and is of order 1, because this is a proper rescaling. Okay, so epsilon to the power k is the order of magnitude of x. And so the idea is behind the method is just to check or evaluate, much better, evaluate the orders of magnitude of the different terms in the governing equation. All right, so what do we have here? Let me just copy the equation here. Epsilon x squared plus x minus 1 is equal to 0. So the first term is epsilon x squared. So it means this is epsilon multiplied by x tilde square multiplied by epsilon to the power 2k. So it means that T1, which is the order of magnitude of the first term, is equal to 2k plus 1. All right, so that's the power of epsilon that you see in the order of magnitude of the first term. Second term, this is x. Okay, so which is nothing but x tilde epsilon to the power k. all right, meaning that the order of magnitude of the second term, which I'm calling T2, all right, so T does not refer to the term itself, but it refers to the order of magnitude of this term is equal to K. Third term, this is minus 1. Well, clearly this one is epsilon to the power 0. So T3 is equal to 0. All right, so now what we can do here is to provide a plot. I'm going to plot them positive from right to left and increasing from top to bottom. That's a little bit unusual compared to how we usually plot. But I'm going to use K on the x-axis. And the reason why I do this is because when K is positive, then we have something small. And when K is negative, we have something large, right? Just as an example here, this is something that would mean 1 over epsilon square, while here we have something that is epsilon. We have 1, and we have 1 over epsilon, all right? So you see that we go from small to large when we go from left to right. Doing the same on the other axis, I'm going to plot here the orders of magnitude of each term. All right, and so the orders of magnitude of each term are gonna be plotted here. And again, same story, we go from large at the top to small at the bottom. All right, meaning for instance that here we have 1 over epsilon, that's large. Here we have 1, and in here we have epsilon. All right, so what we do next is then we just plot T1, T2, T3 in this representation. I can start with T3 because it is very easy. It says T3 is equal to 0. That is this equation. Okay, all of them, of course, are just lines because we plot T as a function of K, and you see that T is always a linear expression of K. So this is very easy to plot. T1, let's come back to that one. When K is equal to 0, should pass through this point, and the slope should be equal to -2, or put differently, when K is -1, we have -1. All right, so it should pass through that point. And when K is equal to 1, it should go through 3. All right, seems good. So we have something like this, that is T1. And T2 is very easy to draw because it should go through 0, 0, and -1, -1, +1, +1, etc., etc. All right, it's a little approximate, but this is how it is. So let me just rewrite T1 over here and T2 out there. All right. And so what does this mean? It means that all possible intersections that we observe over here correspond to points where at least 2 terms have the same order of magnitude, right? Let's start as we did before. Let's assume the first 2 terms, as we did here, have the same order of magnitude. It means T1 and T2 have the same order of magnitude, meaning that we should look for the intersection between T1 and T2. And what did we get? We got this point. And so we found that K is equal to -1. So it means that the order of magnitude of each term is 1 over epsilon. And this is indeed what we saw. before, we saw that the order of magnitude of each term is 1 over epsilon when k is equal to -1, when x is 1 over epsilon. Okay, we can interpret the other intersections exactly in the same manner. We have observed that one intersection corresponds to the root, which is of order 1, and provides leading terms, which are also of order 1. That was the solution we got out there. And we also saw that it was possible to have T1 and T3 with the same order of magnitude, with a root which was of order 1 over square root epsilon. But unfortunately, these two terms were not the leading terms, and the other term, the second term, was actually larger. It is above in this plot. All right, so if it is above in this plot, it means it is larger. And so very quickly then, I've been through all the derivations again, but very quickly then, how do we use this kind of plot? After having drawn the different lines, what we just need to look for is the upper envelope. And the upper envelope of this provides the order of magnitude of the largest term in the governing equation. All right? And what we are interested in is exactly the locations of those intersections corresponding to the highest terms. Okay, so this is the upper envelope. Upper envelope. Keep this one in order to detect which root you're interested in or which roots you want. Find the different kinks, so the intersections in that envelope, and those kinks will correspond to the orders of magnitude of the different values of x that make sense. And for each of them, the ordinates that you can read over here correspond to the order of magnitude of the leading term. All right, so this somehow summarizes in a single chart the information that is necessary to solve the problem. Okay, it is also really interesting because sometimes during the different tests and exams that I used to ask at the end of the year, there's much more than just 3 terms. There might be 4, there might be 5, there might be 6, and sometimes there might be even much more. And so in that case, what you need to do is just to figure out how each term is represented in this graph. Focus only on the upper envelope. And this is a very simple way to simplify the problem you're looking at in order to extract the interesting orders of magnitude. All right, so I hope this was clear enough. There will be now a series of exercises in which you'll be able to practice so that you can get acquainted or get used to the method a little bit more. Okay, I hope you enjoyed, and of course now keep going.